All right, so I'm just going to dump a ton of formulas on you real quick. This is every formula that we'll use for the entire unit that we haven't already covered. So make sure you take notes on this. You should have your formula sheet already, but there may be things you want to add to it, or you may want to put this in a specific page in your notes so you can always just kind of find them all really, really easily and quickly. So the first formulas that we're going to look at is we're going to look at the formulas for kinetic energy. And there's two different forms of kinetic energy we care about in this class. Linear kinetic energy, which is what mostly we'll worry about, and then rotational kinetic energy that we'll talk about a little bit in this unit, and then again when we get to our rotational unit. So the linear kinetic energy, I usually write as either KT as in translational kinetic, or KL as in linear kinetic energy, is equal to 1/2 mv squared, where m is the mass of the object, that's measured in kilograms, and v is the velocity, that's measured in meters per second. So if we kind of pull those together, that would end up being kilograms times meters squared over second squared, which is really a joule. That's how we define our energy units, is in joules. So that's linear kinetic energy. In rotational kinetic energy, Kr, we have 1/2 I times omega squared. I is the rotational inertia of the object. It's how hard it is to spin something. And we'll definitely spend more time on that when we get to rotation. But the units of that are kilogram meter squared. The units of this term, this is the angular velocity, and it is radians per second. So if we pulled that apart, again, we end up with units being joules there. The units are always going to be joules. I'm just kind of trying to reinforce that. Our next thing that we're going to look at is we have gravitational potential energy, grav potential. The variable to represent that, any type of potential energy, we tend to use a U for, and then I'm going to use a lowercase g to say specifically what kind of potential energy we're dealing with here. So that's UG, and the formula for that is m times g times delta y. Delta y, we use that because we're always talking about how far it is from what we've defined as zero. It's very weird to say zero potential energy absolutely. That only would exist at one point in the universe, like whatever the exact center of mass of the universe is. But for practical reasons, we can just say, let's call this spot here zero. So often we would call the ground zero, or we might call the top of a desk zero if we're just doing an experiment on the desk. Or if we're talking about a pendulum, we'll talk about the lowest point it ever gets to. We're going to define y as zero as whatever's convenient to us when we're solving our problems. So this is our height measured in meters. This is acceleration due to gravity or gravitational field strength. So that's meters per second per second. This is our mass in kilograms. So once again, we have something that would be in kilograms times meter squared over second squared, which all works out to be joules. The other form of gravity, this is what we would do if we were talking about things moving through space in orbits and stuff. So we would say that the gravitational potential energy of an object in space is equal to negative g m1 m2 over r squared. Or I'm sorry, just over r. The negative is kind of weird for people, but it actually makes sense if you think about the idea that we want gravitational potential energy to be very, very big when objects are far away. And we want it to get smaller if objects are touching each other because they can't fall any further towards each other. So a negative, so that kind of works. The other issue is the r in the bottom. The r in the bottom means that the closer that they get to each other, the number would be getting smaller, or I'm sorry, would be getting bigger as r gets smaller. So we need the negative sign to counteract that r in the bottom, and it makes it all work out. We'll do problems with that, and hopefully I can explain that better. The next type of energy, we've done gravitational potential and kinetic. Our last mechanical form of energy that we deal with in this class is spring potential energy, spring potential. And again, that's going to be done with a U and then sub S. Sometimes I do U sub K because of this K right here. I'll explain in a sec. So the formula for that is 1/2 kx squared. The K is called the spring constant. We'll do springs more in a couple weeks, but springs are or the spring constant is how stiff the spring is, how hard it is to change its shape. And the units of a spring constant are newtons per meter. The units of x are once again meters, although we have to be careful with x. X is not the length of the spring, it's how much you change the spring's length by from its natural length. So it's not this length that it starts at or this length that it ends at. It's the difference between those two lengths that's our x. And if we pull all that stuff together, that gives us newtons over meters times meters squared, because of the square there, which simplifies to newtons per meter, which is another way of writing a joule. So joule is just the way to like collect all of these different units together, but mathematically they all always work out to be the same thing anyways. So those are our three types of energy and some different formulas that are important for each of them. But if we're talking about changing the energy of a system, then we're talking about work. And as soon as we're talking about work, we have a couple other formulas to talk about. The first and most important version of the work formula is work is the change of energy. If I tell you that an object started at rest and now it's moving this fast, and I ask how much work was done, the right way to figure it out is to do kinetic energy stuff, figure out how much kinetic energy changed, and then you know exactly how much work was done on it. That's the right way to do the work calculation. And that's the one that I want you guys to default. Always look at the change in energy and figure out the work. But the whole idea of work is applying a force to add or remove energy from the system. So we also have this formula for it. Work is equal to force that's parallel to displacement. I'll deal with this a little bit more in the All About Work video. But if work is measured in units of newtons and displacement is measured in units of meters, once again, we ended up with a Newton meter, and it works out that work is also measured in joules. That makes sense because work is the change of energy. So if energy is measured in joules, then work would also be measured in joules. We're doing all joules here. And finally, the last formula, if the force isn't parallel to the displacement, if it's at an angle, we'll get this formula here. And this is the ugliest one in the entire unit, but I will explain why you use it and the very rare times you use it in the All About Work video. The last thing that I want to say about this on the formula junk, this is our last math fact that we need to know, is that both work and energy are scalars. That means that they do not have a direction. You can have kinetic energy, but it doesn't matter what direction the kinetic energy is in. The minute that we square velocity, if it was positive or negative, suddenly that got wiped out by squaring it. And that happens to everything that we do with work problems and energy problems. They have no direction. We just know whether we have energy or we don't have energy. Even if we have negative energy, that's still not telling us a direction. That's just telling us that energy has moved out below what we previously called zero. So work and energy are both scalar quantities. We've been dealing with vector quantities before now, and all the quantities that we're using to calculate work and energy tend to be vector quantities, but when we multiply them together, it washes out and they turn into scalar quantities. So thank you for watching this video. I hope all these definitions are helpful to you guys, and we'll be using them a lot in class moving forward.